last test.
I didn't promise that.
This one's really gonna take.
Unless we got a final.
The test? Do you want it to be before spring break?
No.
Okay, then let's worry about it after.
So,
Okay.
Is there any chance if, like,
Close.
somehow are in the 90s,
we
we
would
just
make
like
closer.
make the final for this year's like a project or something?
Please.
What
We've been through 4 years of this.
What if the final is the same format as it was first semester?
No, but then that's math related. Can I just draw
Yeah, I'm good with that.
What was in the first?
He gave us use of the study guide.
Oh, yeah, but I still.
So then we still have to do the study guide.
Hey. Like I can only like.
Can the final be like, what was your favorite part about the math class? What was your least favorite part?
Look,
did you learn?
here's the thing. I actually have to turn in all of the stuff that I give you guys. Someone possibly could look at it. I don't know that they ever would, but they might. Like your finals and stuff, you turn those in. So like it should at least look like stuff that we did. Now, I'm going to give you a study guide that if you turn it in, you can use on the final, and it'll be very helpful to you. And you have some like.
I want the exact same number, like the exact same number.
Can it just not be as thick?
10 questions. Or one question each chapter.
The senior ed is just really.
I know.
It's so bad.
Do you think it's going to get better?
No.
No. Here's the thing. You know why it's bad? Because you're looking at like May 14th or whatever, after all the tests and everything are done. Don't look at that date. Just worry about today. Just get through today, and do a good job today.
That's all I'm saying.
And just
I think one day at a time.
look. I know that like this is Mr. Kulik just trying to do what's in his best interest. This is like life. This is life advice. Like stop. You can make a long-term plan, but after that long-term plan is made, you just worry about your day-to-day. And just do the best job you can on that day. And if you keep stacking best days together, everything turns out okay. And I know it's real tempting to just like,
There's nothing like.
I just want to pack it in. But here's the thing, you're not done. And you can't like just not, you can't just be done right now, even though that's what you want. You're stuck here. You guys haven't been graded. You don't know what you got on it.
I do.
You're the only one that can.
I even studied for it. Like I sat down and
I'm really glad you did that.
I didn't even know my own test. I just went 5 on.
I'm gonna keep powering.
Yeah, I'm not gonna lie,
I don't know
I'm
what's
gonna
going on.
All right. So just like, let's just try to do the best we can with the time we have remaining together. Okay? I'll keep in mind what grade you're in, but like, you keep in mind that we just can't do nothing for a month and a half.
Oh yeah, for sure.
Right? Like we like.
or like the colors where you do a subtraction problem and that's what color you color. Have you seen that?
Can we bring back geometry? Because
I
that
do
was fun.
love them. Have you seen where I was like 1 through 10 you color red?
No, I mean I've seen my daughter in pre-K's homework.
Can you give us those?
Like I'm good with like color number 1.
Solve the function
Color number
and then
2.
color in the graph.
Exactly. And then
What is 1 plus 2
you can make a
equal
pretty
green?
picture. I can get final.
Final.
Okay. You know what? If that's what you want, I can make it. You're not gonna like it though.
I'm good.
Is I'm gonna find my daughter's like color by number 1 through 20, and then I'll just create equations that you have to solve to figure out what color what the color goes with.
How many questions are there going to be?
And some of them might have more than one solution. You know, it might not go as well as you think it's going to, even though you have to color some stuff. All right, let's get through this piece today. Why not? We've been here for 5 minutes. All right. So chapter 14. We're going to take and talk about rational functions. What is a rational function? Well, it's just one polynomial over another polynomial. Blaine, I have a stack of printer paper up there. You're welcome to.
I don't know what I did with all the paper.
You probably did your math homework on it.
Yeah.
Right? Is that what happened to it?
For sure.
All those math assignments you've been doing.
Yeah, all of them are missing.
You're all the way over there.
So, the core skill that we're going to be looking at today is going to be graphing these rational functions. But before we do that, we need to talk a little bit about domains, because that's going to be an important piece of being able to graph these things effectively. So remember back to first semester, we found domains already. So to find a domain, we have to ask ourselves, when is this function undefined? So let's first look at the operations going on in the function. What operations do we see in this f of x here? What operations? What? Division's one? Absolutely. Multiplication, addition, subtraction. Those are the four. Of those four operations, addition, subtraction, multiplication, division, bless you. Which is the only one that can produce an undefined result? Division. That's the only one we care about. Okay? When can division create an undefined result? When we divide by 0. So the domain, all we're going to worry about is when the denominator is equal to 0, or in other words, our domain is going to be everything except when we get that undefined result when the denominator is 0. So we can set that not equal to 0, we add 1 to both sides and divide by 2, we get 1/2. So my domain is going to be everything except for 1/2. That's all the numbers up to 1/2. And then all the numbers after 1/2. I wrote this in interval notation. Notice that I used a parenthesis on the 1/2 rather than a bracket, because the parenthesis means that value is not included. Right? So that's everything except for 1/2. Does everybody feel okay kind of doing that one? Not bad, I would hope. Let's do another that's a little less trivial. Let's try this one. Okay, how do I start? Who can tell me? What's it? Thank you. The denominator. Yeah, we'll set it not equal to 0. So how do we solve x cubed minus 4x not equal to 0? Well, there's no squares. It's not a perfect square, so square rooting both sides is a bad idea. I would not cube root it because, again, you can't cube root individual terms. That minus is kind of creating a problem for you and trying to cube root. If it was just x cubed equals 0, sure. But the minus 4 there is going to be a problem for you. I'll give you a hint. It starts with an F. Factor. Great. How do I factor x cubed minus 4x? Great. Start by taking out an x. Now, if I look at that x squared minus 4, what do you notice you can do with that? Well, let's continue factoring.
It'd just be like x minus 2, x plus 3.
Fantastic. Yes. That's a difference of 2 squares. And now that it's completely factored, we can set each factor not equal to 0 and then solve them independently. Everybody's okay there? Kate, if you had elected here to do this, that's okay, but I worry about the plus or minus when you square root both sides being forgotten. That's why I always trying to get you to factor instead. But that would not be incorrect, although there's a good opportunity to goof that up. All right. So let's start writing our domain. We go negative infinity 2. What should be the next number in our interval? Negative 2. Great. Why did you pick negative 2? Because it's the smallest number of the list. So it's the next one closest. And we'll go negative 2 to 0. Very good. And then, nope. We will do 2 to infinity, but there's something you've forgotten. 0 to 2. That's probably as hard as it gets. Everybody's okay? Okay. So we're going to now talk specifically about graphing rational functions. To do that, we're going to find the key features and use those to construct a graph rather than creating a table of points. That can be kind of a hassle because, well, these things can be pretty complicated looking and it's not always obvious what points to even pick. What we're going to do is actually going to be, in a way, I think, simpler to get a decent graph out of this. So the first key feature we're going to look for are discontinuities. There are 2 types of discontinuities. We have vertical asymptotes. To find those, we're going to set the reduced denominator equal to 0 and solve. The other type of discontinuity we can see is called a removable discontinuity. And here we're going to set any factors completely reduced from the denominator equal to 0 and solve. So quick little example or two here. Let's say we have x squared plus 3x plus 2 over x squared minus 2x minus 3. And we're just looking for the discontinuities here, or discontinuity. We don't know how many there's going to be. There could be none. Since both vertical asymptotes and removal discontinuities require reducing, let's start by trying to do that. What do I need to do to reduce a rational function? Give you a hint, it starts with an F. Factor. Great. How does x squared plus 3x plus 2 factor? Yes, x plus 2, x plus 1. Remember, multiplies and then adds. How about the denominator? Great. Now, take a look at our factored form. What do you notice? What do you notice in that factored form? Again, what are we trying to do here? Reduce. Is there anything to reduce here? The x plus 1s. Everybody okay there? So our vertical asymptotes are going to be anything, or it's going to be the reduced denominator set equal to 0. Pretty cool there. Pretty easy. The removable discontinuity is going to be any factors completely reduced from the denominator. Notice that the x plus 1, when we cross that out, there's no more x plus 1s left, right? Everybody agree? So that is completely reduced. That'll become my removable or I'll use to find my removable discontinuity. But a removable discontinuity is kind of like a point. So it needs to have a y-coordinate also. To find its y-coordinate, I'm just going to take that x that I found and plug it into the reduced version. Is everybody okay there? Question. Does every rational function have to have a removable discontinuity? No. How do you know right away if you're not going to have one? If you can't do any reducing, you can't have a removable discontinuity, right? Everybody agree? Does every rational function have to have a vertical asymptote? No. Okay, what could happen to not give you one? You're right. What if the denominator was x squared plus 1? What's the solution to that going to be? If I solve that for x, you get plus or minus I, right? Those are imaginary. Those don't count as asymptotes because they don't appear anywhere on an xy axis. That's an example of a polynomial that might have, or that has no vertical asymptotes. Everybody agree? Could a rational function have more than one vertical asymptote? Absolutely, right? If we just take the previous example, except we make the numerator just 1, then the denominator is x minus 3 times x plus 1. It would have 2 vertical asymptotes. Could you have 2 removable discontinuities? Sure, the same idea, but I'm not going to cook up an example just because it's kind of a hassle, but certainly that could happen as well. Here's the big $100,000 question. Let's say that we have a rational function that can be reduced. Does that guarantee I have a removable discontinuity? No. What could happen? Let's say I can reduce a factor that includes an x. Now, does it guarantee that I have a removable discontinuity? What's the vertical asymptote going to be here? -1, correct? What's the removable discontinuity going to be? There isn't one. Why doesn't that x plus 1 count? Yeah, remember it says completely reduced from the denominator. After I reduce the x plus 1, I still have an x plus 1 in my denominator. It has not been completely reduced. Therefore, it cannot count as a removable discontinuity. It'll just end up being a vertical asymptote. Everybody catch that? So just because we reduce doesn't guarantee that we have a removable discontinuity. Okie dokies, artichokes. All right. Next up are asymptote end behaviors. And there are 3 of these. So and the way we decide which one of the 3 is happening is we look at the degree of the numerator and the denominator. So if the degree of the numerator is less than the degree of the denominator, then the, I want to use the same vocabulary that I used in the notes here. Sorry. Oh, this is called end behavior asymptotes, right? Let me double check. Yeah, okay. So if the degree of the numerator is less than the degree of the denominator, we always have an end behavior asymptote at y equals 0. If the degree of the numerator equals the degree of the denominator, then the end behavior asymptote is y equals a sub n over b sub n, where a sub n is the leading coefficient of the numerator, and b sub n is the leading coefficient of the denominator. And then the last case, if the degree for the numerator is greater than the degree for the denominator, then the end behavior asymptote is y equals the quotient of the numerator divided by the denominator. Yeah, this screams, this like list of like what are the key features and how to find them screams note card stuff to me. We'll do examples of all this stuff in a second. The next key feature are the zeros. We set the reduced numerator equal to 0 and solve. Those will give you the zeros or x-intercepts. And then the lastly is the y-intercept. We plug 0 in for x and evaluate. You ready to do some examples here, my dudes? No? The sooner we get through the examples, the sooner I can leave you alone. We can just be done. Does that change your tune? Oh, okay. If you need a minute, just tell me to like, hey, hold up a second. I'm trying to still write. That's fair. Sometimes I just get excited about the math, you know?
Yeah. Some math.
Look, if you can't get excited about your everyday life, try a little harder, you know? Just saying, you're in charge of how you feel. Your brain, Your body will do what your brain tells it to. All right. Graph the rational function. First thing I'm going to do is I'm going to check to see if I reduce this, because everything I'm asked to do with this needs to look at the reduced version. And pretty quickly I can see that although I can factor the denominator, nothing reduces. So we'll start by finding our vertical asymptotes. I'll take those two factors from the denominator, set them both equal to 0 and solve to give me 2 vertical asymptotes. Since there was no reducing to do, I obviously can't get a removable discontinuity. For the end behavior asymptote, what's the degree for the numerator? Excellent. And what's the degree for the denominator? 2. So since the degree of the numerator is less than the degree of the denominator, I know it's y equals 0. Always y equals 0 in that situation. That's my favorite one. And then for the zeros, I'm going to take the numerator, set it equal to 0. And I always write my zeros as a point, like, because I don't want to confuse it with a vertical asymptote when I go to graph this later. And the last thing I want is my y-intercept. So x is always set equal to 0. So I get y is 1/4, so I have the point 0, 1/4. Everybody good with how I cooked up these key features? All right. Thought that was pretty funny, apparently. All right, let's draw ourselves a graph. So I'm going to start by drawing in my asymptotes. I'm going to use half a unit as my scale. Everybody happy with what I drew there? Okay. I'm going to go ahead and plot my 2 points. And now I'm going to try to draw the rest of my graph. So keep in mind, starting at the left-hand side, that my graph shouldn't cross my asymptotes. So I know it's either going to look like this or like that. For me to be able to tell, what I'll do is I'll pick a test value from over here, say like -3, and I'll go ahead and plug it in up here. So in the numerator, I get a negative, -3 minus 1. In the denominator, I get a negative times a negative, specifically -5 times -1. So I have negative over positive. That result is negative. I don't care what the number is. I just care that it was negative, because that tells me that that point would be down there. I just picked it. Somewhere over here, I just picked an x value that's somewhere over there. So like -3 was over there. My units are half.
That's awesome.
Okay. I announced it when I drew it, but I said it, didn't write it, so that's fair. So that's that part of the graph. Now from here, I'm either going to have something that does this, or something that does that. And I actually know which one it's got to be without having to do a test value, because the only place that my graph should be crossing the x-axis is right here. So that can't possibly be part of my graph because I have an unaccounted for 0. Yeah, go for it, homie. Everybody feel good there? So now my graph is either going to continue down like this or bounce back up. To check, I'm going to pick an x value between 1 and 2, so like 1.5. I'll go back up here. When I plug 1.5, I get a positive in the numerator, and then a negative times a positive in the denominator. Positive over negative is negative. So I know that I want the piece below the x-axis. And then the last part here, it's going to be one of those two. Again, I'm just going to pick a test value, maybe 3. If I plug it in, I get positive on top over positive times positive, so all positive. So I need to jump the negative part of my graph, and there's my picture. Is everybody okay with that? And what I did there, if you want to actually compute those test values to a point and plot the point and draw it through the point, that's okay, but you don't need to. If it's easier for you to do it that way and you need something a little bit more concrete, totally acceptable to do that. So far, so good? This is the one that included or was necessary to do the most amount of testing. I think the other ones, the testing is even easier. Oops. Okay, let's take a look at this one. 2 minus x over x plus 3. Can I reduce that? Definitely not, right? I can tell right away because the polynomials are both degree 1 and their leading coefficients are plus or minus 1. So no reducing really to do there. Everybody's good? Okay, vertical asymptotes, denominator set equal to 0. What do we get? -3. If there's no reducing, there can be no removables. My end behavior asymptote, well, the degree for the numerator, I already spilled the beans, was 1. And the same for the degree of the denominator. So my asymptote should be the leading coefficient of the numerator, which is what's the leading coefficient of the numerator? Nope. Nope. What? Nope.
-1.
-1. Great. And the leading coefficient in the denominator is?
3.
Nope.
1.
1. So y equals -1.
Why is it -1? Oh, yeah.
Because there's a 1 in front of the x.
Yeah.
Okay.
Yeah.
Well, you ask a silly question, you get a silly answer, right? It's not silly. No reason it can't be fun, though, right? Yeah. Dom's having a great time.
I saw that now.
Okay. Those are my key features. Everybody good with how I came up with them? Yeah? Okay. I didn't talk much through the y-intercept, but it's like it's a y-intercept, guys. Just plug in 0 in. Okay. I'll draw in my asymptotes first. So I have -3, 1, 2, 3, 4, 5. Again, I'm going to go by halvesies again. Okay. So if I start on the left side, I know that my graph is either going to look like this or like this. Everybody's okay? I know immediately which one it has to be. Can't be this one because the only x-intercept I have should be 2, 0. That definitely ain't 2, 0, so that can't be my graph. Everybody good with how I came up with that? Those zeros are your best friends. They can really help you eliminate like what is going on. Over here, well, it's got to go through those 2 points, so it's just got to look like that. And I'm donezo's. Is that okay? Do one more, and I am through with you guys. You're through with me too? Feels like that happened like a month ago.
Yeah.
We can be real.
Class.
It's my class, not me. I don't know if that's any better or not. Yeah. All right. Again, start the same way. We try to reduce. That numerator is factorable, but nothing can reduce, so whatever. Vertical asymptotes, the denominator set equal to 0. So -2. No reducing means no removables. Hey, these removables, do these happen very often? We've done 3 examples. We haven't seen one yet. Probably not happen very often. My end behavior asymptote, I notice the degree of the numerator is 2, which is bigger than the degree of the denominator, which is 1. What did I have to do for that situation? It said I need to find the quotient of the numerator divided by the denominator. Oh no, I'm dividing 2 polynomials. What are the 2 ways I can do that?
-5 plus 1.
I can do long division, or I can do synthetic division. Which one would we prefer to do? Synthetic. Can I do synthetic division in this case?
X squared minus 5x plus 1 x.
Hey, you're just saying stuff now.
No, isn't that how we did the thing?
So we can do synthetic division here
That's not what I'm talking about.
because the divisor has leading coefficient 1 and degree 1. Just when you thought you were done with all that stuff. That part's the quotient.
Well, can't we just split that guy up?
Split that guy up.
Which one are we doing? We're doing the top or bottom?
I did the numerator divided by the
Or
denominator.
you already split the top?
I didn't split anything up. Oh, I factored it, yes, to check to see if I could reduce it.
Never mind.
I did that already. Is that what you were trying to do?
That's all I was doing, yeah.
Okay. Okay. Yeah, we checked that just to see if we could reduce or not. Okay. Zeros, again, I'm going to take the numerator, or the factors from the numerator anyway, since I've already factored it. Set them equal to 0 and solve. Oops. So I have 2 x-intercepts. everybody okay with what I did there? To get my key features. This is kind of the worst case scenario because you have to do possibly long division. Hopefully, it'll just be synthetic. All right. Let's draw. Put in my asymptotes first. So I got -2, 1, 2, 3. I'm going to do half units again. Oh no, now I have to graph y equals x minus 6. How do I graph that? What kind of graph is that going to make? It's a straight line, right? Because it's a y equals mx plus b. How many points do I need to graph a straight line? 2. So I'll pick 0 for x. That'll give me -6. So 0, -6 is 1 point. And I'll pick 6 for x. That'll give me 6, 0 for another point. I just picked those two arbitrarily. You can pick whatever you want. 1, 2, 3, 4, 5, 6. Okay. Then I have -1, 0, and then 5, 0, and then 0, -2.5. 5. Ooh, boys, he's do a better job there, Kulik. Ugh. 1, 2, 3, 4, 5. So that piece has to look something like that, right? To connect those 3 points. Now the question becomes, is the other part of my graph look like this or like that? You can tell without having to do a test. Which one can't it be? The one on top or the one on bottom? Can't be the top. Why? The top has an x-intercept. But I've already graphed all the x-intercepts for this function, correct? Can't be another x-intercept over there. I would have found it. So it has to be this one down here. Those x-intercepts are your best friends on figuring out which one it is. They help a lot. What do you guys think? You're thrilled. So I think I want you guys to do 1 through 8 and then, let's see, 13 to 24. One through 8 are just like finding the domain or the asymptotes and stuff like that. It's like not the whole thing. What do you guys think? Everybody okay?
Yeah, I'll do it.
I'll take it. Begrudgingly. All right, I'm going to stop talking now.